So before we get started, I'm just gonna go over a little brief overview, kind of just a little bit more about me in case you don't know enough. My name's Joe. I went to Pitt a few years ago and studied chemical engineering, but right now I actually work as a software engineer. So the way that all kind of shook out was, liked engineering in school, but the thing I liked most about my time at Pitt was taking OChem and then pretty much finding any excuse to do more OChem, whether it was, TAing, helping friends, tutoring, whatever. If someone was doing carbon-based chemistry and needed any help, I was there, plain and simple. So my junior year, started getting some programming, and I thought to myself, a cool project might be, let me automate myself. Let me make my own little mini Khan Academy just for OChem specifically. So that's what I did, and that's how JoChem was born. So it's a little weird. I'm a few years out of Pitt now. So one thing I did a very poor job of while I was at Pitt and starting this project was, the social media side of stuff, like continuously creating content and things like that. So that's what I'm trying to get better at this year. So if you don't already, follow my Instagram at jochem_io and my YouTube channel, which are all linked on my About page on JoChem. And I personally don't like doing that stuff, but I want people to use this, JoChem. I want anyone that is taking organic chemistry and wants extra help or practice for whatever their goal might be. If they want to go to med school, dental school, be a physician's assistant. I like this subject so much, and I don't want it to be something that stops people from doing what their goals are. Instead, I think it's such a cool subject, and I think it's a really awesome way to problem solve. So I want them to have a positive experience and remember their time doing OChem is something that was challenging, that kind of made them a better thinker. So I think that might have been everything I wanted to say. So I will be doing these live review sessions for every exam this fall and then the spring. So having said that, before I I announce these, whatever, right now I've prepared a review, but this is very much for the people like you that are watching it right now. If you guys have problems you want to solve, DM them to me on Instagram, or I have an email address linked on my About page as well. It's really corny. It's organicchemistry@gmail.com. Send them my way. I'm a normal person. I work, friends and family. So yeah, if you this would be the perfect time to send me questions like that. And I'm going to try and do my best to kind of monitor if anyone's even saying anything in the chat, to look at that. But for the future, these reviews are for you. They're not for me to just talk and talk and talk and talk. And I think, I always think certain topics and things are important, but I obviously I'm just one person and I'm not your professor, right? Whether you go to Pitt or not. So send me the problems that you're struggling with or that you think will end up on your test that you might not know the best way to go about. Okay? All right, so that's kind of the little about spiel I had before. And of course, since I'm so bad at always remembering it, whether you're taking OChem or you have a friend taking OChem, please send them the link to the website, live reviews, whatever. I'm just someone that wants to help other people crush OChem. Okay, so for this review, pretty much it's just going to cover, I hope, the other thing is also, I don't know when people's exams are, so I picked this day to do the live review. I have no idea if test has already happened or if it's coming up. Something you can just tell me in a DM or whatever. Just going to do the Gen Chem review stuff, then all the kind of intro to alkane stuff. So obviously we'll do going to blow through Lewis structures, resonance, hybridization, all that good jazz, thermodynamic diagrams. And then we'll do common naming, regular naming. I know it's boring, but it's important. Then we're going to kind of delve into Newman Projections, Cyclohexane, stability. Obviously, we're going to talk about free radical halogenation reactions, chlorination, and bromination. The selectivity things that go on between chlorination and bromination, who's less picky. And we're going to kind of round it out by talking about Hammonds Postulate. I didn't want to include stereochem on this for this review because the other thing is too, I love to talk, if you couldn't tell from my videos, and that's why I blocked off an hour and a half for this thing. So I'm going to try and stay on track. with the allotted time, or maybe even cut. I don't want you to just be sitting waiting like, when is he going to get to X? I'm only here for this. I'm going to make sure this is a tight, efficient review. Yeah, so without further ado, what I was first thinking about starting off with, just to kind of ease into it, you know what I mean, is let's do like a Lewis diagram, Lewis structure problem. So I know that sounds super lame, probably like, Joe, come on, that's first grade, wumbo, right? But I think if anything, nice little win to get us started. All right, so I have my handy dandy notepad of just the things I want to do today. So, all right. I feel like this is such a classic draw the Lewis structure type of problem. Like this thing in particular, this is the azide ion. All right, so with Lewis structures, what we need to do first, the first thing we do, and some people, most of the time, they give you the skeletal like layout of this. It's just 3 nitrogens in a row. But we need to count how many electrons we're working with, right? Because that's what we're going to do in this Lewis structure problem, is basically illustrate and fill in how these are all connected and who's sharing what electrons. All right, so obviously from the periodic table, which you would know nitrogen comes from the 5th column, right? So we have each nitrogen brings 5 electrons to the table, so we know we got 15 electrons from that. However, I'm thinking you guys are probably sitting in your computers thinking, but that's not all we have. We have this extra negative charge, right? So that's what, if it's negative, you add that many electrons. If it's positive, right, you would kind of subtract that away. So in this case, we have 1 electron from the negative charge, giving us a grand total of 16 electrons to work with. So that's pretty cool. All right, so I'm going to show you guys, and this is like the foolproof, you can't mess it up, any type of way to draw a Lewis structure method. Just give everybody 8, right? Because we're trying to fill octets. Give everybody 8 electrons, and we're definitely going to use too many, but then we'll start scaling things back, and you'll see how we do this. So, okay, so giving everybody 8, right? Because you can see 2, 4, 6, 8. This nitrogen has a full octet. 2, 4, 6, 8. Middle guy has a full octet. 2, 4, 6, 8. This gal on the end, all full. Everyone's happy. However, did we use the electrons we were allotted, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Looks like we used 4 more electrons than we actually had, right? So that's a no-go. So what we're going to do is we need to consolidate, right? We need to fill everyone's octet, but within the constraints of the electrons we have. So the easy way to do that is just erase a pair from 2 people, 2 neighbors, make that a double bond, right? Because now there's still 2, 4, 6, 8. 2, 4, 6, 8 for the middle person, 2, 4, 6, 8 on the end, right? And if we count up our total number of electrons one more time, 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, closer, right? But now we're just going to do it one more time, and bam. 2, 4, 6, 8. Good, full octet. 2, 4, 6, 8, full octet. 2, 4, 6, 8, full octet right here. Okay, however, so that's the Lewis structure part. I'm sure that was easy for you guys, but what I think is a little bit more interesting now is, okay, that was the baby stuff. So now let's kind of bring in another topic here, get a little bit more bang for our buck on this example. So let's talk about formal charges. So formal charges is the idea that, here's like the summary. The amount of electrons that an atom brings to the table, right, is like you can count up how many it actually ends up having control of in a given structure, and that's its formal charge. Let's actually see this in an example. So nitrogen comes from the 5th column, right? We established that when we were counting electrons. So I'm going to count up how many electrons this nitrogen controls. If it's a lone pair, this nitrogen full straight up owns that electron. But if it's a covalent bond, then these count as half, or like they count as 1, because in this bond there are 2 electrons, but it's shared, right? So this nitrogen, he comes in with 5, and he is actually in control of 1, 2, 3, 4, 5, 6. Because we're good at math, we know that's -1. So the formal charge for this nitrogen is a minus. Okay, let's do this for everybody. So this nitrogen comes in with 5. He's in control of 1, 2, 3, 4, because I'm counting each of those bonds as 1. Bada bing, bada boom. That's a +1, right? Bam. Okay. And we can even see that this nitrogen on the end looks exactly like the one over here, but I'll even count it up. He comes in with 5. 1, 2, 3, 4, 5, 6. minus 1 as well. You know you've done your formal charges correctly if they add up to the overall charge of your structure. Right here we have minus plus minus, which overall is net -1. Bingo, that's what we have for the structure, so we know we did our formal charges correctly. Okay. However, so one more thing we can do with this example before we move on is someone might ask you, draw the best Lewis structure. Draw the most stable thing, right? So if we look at, which is basically a fancier way of saying minimize formal charges, right? We don't want something to have a charge that doesn't have to. If we can make it neutral, right? Nature likes stability, right? And when things are charged, they're reactive. That's not, oh boy, that's not being stable. That's instability, right? Instability. So English is hard. So can we make this better? And the answer, I hope you're standing at your computer, is shaking your head saying, yeah, we definitely can. So what we can do instead is we can, and this is through resonance, but I'm going to do a resonance example right after this, is if we actually had, so this nitrogen almost controls too many electrons, right? And this nitrogen kind of like wants a little bit more. So if we just rearranged, if we just put these electrons right here, if I use the double-headed arrow, because I'm moving 2 electrons right here, and I drew a double-headed arrow right here saying, ooh, look at me, I'm drawing resonance. I didn't move this electron pair at all. I'll actually keep him at the bottom, even though it doesn't matter where I draw him. Now I have a triple bond here. Didn't touch the, ooh, what am I doing? I'm gonna break the octet rule. Oh boy, that's not good. Oh, okay. Sorry, guys. What we could do is we could swing these in, and then we'd have to kick these out over here. I am so sorry. It's a Sunday. So the other structure we could draw would be this right here. So this nitrogen is now in control of 1, 2, 3, 4, 5. He's neutral. 1, 2, 3, 4, plus right here, and a minus 2 over here. So you can make the case that this structure is a little bit better because now we actually just have 2 atoms with charges on them instead of 3. Yeah, sorry about that. That was a little rough. Okay, so just an example of doing the Lewis structure, drawing some resonance, and when you do that, you can compare your 2 structures and pick the best one based on how formal charges are created, distributed, whatever. Okay, so what I'm going to do, I'm just going to look at the chat because I never do that. Okay, it looks like no one's talking, which is fine. So I'm just going to go ahead. So that was the Lewis structure example. So let's move on to something a little bit more exciting, and let's do some resonance. Hope everyone is having a lovely Sunday. Okay. All right, so we did Lewis structure, we did a Lewis structure, and we saw how we could have electrons move across a network of atoms, right? So let's do something a little bit more challenging with resonance. So I'm going to go ahead and draw this structure right here. Okay, so if someone gives you this, they might ask you, go ahead and draw all of the resonance structures possible. All right, so what we can do is always when you draw resonance, draw a double-headed arrow like this. That is the universal. Look at me, I'm drawing resonance. So what we can do is with this, so the kind of rule of thumb is with positive charges, if this were to be a positive charge like this, you would want to move electrons to that charge. However, this is a negative example. So the rule of thumb is we're going to be moving electrons and bouncing other electrons away from where we're moving because like charges repel, right? So what we're going to do here, and the beauty of resonance is that you're literally illustrating what's happening. So if you do something whack, you're going to see what whack thing you did. So what I'm going to do is let's just see if we can move these electrons right here. I'm going to move it from a lone pair right here, which is why I started the base of my arrow here, which is how we always do that, and we ended it with a double-headed arrow. So this is me saying this lone pair is about to become a double bond. So we can stop at this point and think to ourselves, do we need to do anything else? Did we kind of break the octet rule? Are we going to cause any problems if I just leave that the way it is? And the answer is yes. because right here at this carbon, these are these two hydrogens that we are implied, we don't draw them. This carbon right here, 1, 2, 3, 4, or 1, 2, 3, oh man, 1, 2, 3, 4 bonds. Oh my gosh, I'm so sorry guys. I'm making some rookie mistakes. 1H, oof. All right, 1, 2, 3, 4 bonds. That's good, full octet. The moment this electron, this lone pair becomes a double bond, we're gonna have problems, right? Because we're gonna go from having 4 bonds to 5. So we have to do something extra before we just kind of call it quits for this one resonance move. And what we're gonna do is I can take this double bond right here and I can pop him up as a lone pair on that carbon. So basically we're just taking a lone pair, making a double bond, taking a different double bond and popping it up as a lone pair. So let's draw the result of our arrows. Hopefully I can stop making some real dumb mistakes. Didn't touch anything inside the ring, so I'm going to leave those bonds the way they are. And 1, 2, 3, 4 carbons off the ring. And the beautiful part is, draw what your arrows illustrate you're going to do. Double bond right here, lone pair right there. Awesome. Okay, so the best part is, so that is a valid resonance move. Yay, look at us, we're doing stuff. Let's keep going. We can do more resonance here. So what I can do with this lone pair is I'm going to make it a double bond right here. And we have to think to ourselves, is that like, are we going to break the octet rule anywhere? Do we have to do anything? The answer is obviously yes. So this carbon right here, I'll make sure I count bonds right this time. He has 1, 2, 3, 4 bonds right now. No hydrogens. He's about to have 5. So I hope you're guessing what we're going to do. We're going to take this double bond right here. And since he's the one that needs to have less of a bond, we're going to pop it up as a lone pair right there. Double-headed arrow right here. Going to draw my new resonance structure right here. Lone pair is now here. Double bond, that's brand new, is right here because that's what my arrow is illustrating we're about to do. And I didn't touch any of this lovely stuff over there. So now we're just going to do ring around the rosy, right? Because we have a few more resonance structures we can draw. Double-headed arrow right here. I'm just going to swing these down right here. And also this is me being a stickler. But make sure when you're drawing arrows, especially when you're just doing lone pairs to bonds, that they're very clear where these guys are going. Like make sure it's right in between here. Don't accidentally do something where you do like this, because then some mean person grading your test is going to say like, oh, nope, they're just trying to move the electron pair from here to here, but that's not what you were trying to do. So just be very careful with where your arrows are pointing, because OChem's hard enough. We don't need to lose extra points wherever the points are easy to grab, okay? So if I do that, I'm going to have to bump this double bond up as a lone pair right here, because this carbon will break the octet rule. So let's keep going. Didn't touch that bond at all. Made a bond brand new right here. Have a lone pair right here. And now we have this right here because we didn't touch anything outside of the ring. And we can do this one more time. Double-headed arrow because we're drawing resonance. Let's swing this electron pair down, make a double bond right here. Let's take this double bond right here and pop it up as a lone pair right there. And what that will look like is double bond right here. Didn't touch double bond over there. Got a lone pair right here. And didn't touch anything outside the ring as well. So there's going to be no surprise on your first test, gang. You're definitely going to have to draw some resonance. So if you're not feeling comfortable, if you don't feel like you can sit down and comfortably figure out some resonance right off the bat, I highly recommend that you just do a bunch of problems until you feel like it's clockwork. What's funny is I remember when I took OChem in high school with the great Mr. Long. If you're watching Mr. Long, you're the man. But I remember doing some resonance, took a resonance quiz, failed it terribly, thought to myself, yeah, maybe this isn't for me. So I just had to do more resonance. So just make sure you put the time in, because resonance never goes away, ever. Okay, so this was, we'll do a real quick example with positive charges, but with the negative situation, you're just going to be moving electrons towards other electrons, and you're just going to have to bounce them away. Move double bonds to lone pairs so you don't break the octet rule. Okay, so we'll just do a real quick positive one, because I think the positive situation is a little bit more intuitive, at least to me. This will just be a small one. Okay, So when we have a situation like this, what I meant by moving positive charges, moving electrons towards positive charges, is that this carbon, right, because he has a positive charge, and I'll draw this a little bit further away, he's a carbon, right? So he comes from the fourth column, so he comes in with 4, and if we see a positive charge here, that means if these are all his bonds, 1, 2, 3, he's in control of 3. That's why he has the +1, because he only has 3 bonds. Okay, and we would call those carbocations. So he has 3 bonds, he can accept some electrons. So one of the resonance moves we can make is actually just taking this double bond and moving it from here to here. So basically this carbon is still a part of the double bond. However, he's now going to be a part of the double bond, and this carbon right here, he's a little SOL. He's going to lose out. But that's okay. We can draw the result of our resonance. We got 6 carbons. I have a double bond here now. Didn't touch the double bond here. And with the thing with resonance is you're not adding or subtracting charge, right? You're just rearranging charge. So you should, before and after any resonance move, it should be the same charge on both sides of your resonance arrow. If you don't have that, if we somehow ended up with a 2+ charge here, that's bad moves. Like that's a bad sign, because that means we accidentally added a bond, forgot to draw a bond, we lost electrons along the way. So what I didn't draw is that this carbon right here now, he just has 3 bonds, so he has the plus now, which is good because we didn't lose any charge in this resonance move. And I'm hoping you guys can see we can do this one more time. Double-headed arrow, look at me, we're drawing resonance. Take this double bond right here. It's going to move it right here. And didn't move this at all. This moved over here. And I hope you're seeing that there's these 2 implied hydrogens here. This carbon now has that plus charge. And yay, look at us. We have a plus charge on every resonance structure. And of course, this is a little harder to get tested on, but just remember, the idea of resonance is when, in this case, this carbon has a plus charge, right? But nature likes stability. Nature will do anything it can to be lower energy, more predictable, more stable. So because of the network of double bonds we have next to this charge, right? This structure just doesn't look like this all the time. It's never just like this with this positive charge completely on this carbon. It looks like this, this, and this, a mixture at any given time, right? So that way, it's not like this carbon has a plus charge all the time, or this carbon has a plus charge all the time, or this one. They're all going to have some partial charge because they're a mixture at any given time. Okay, cool. That is the little resonance spiel. So just make sure you do it because it's super important. It's never going to go away, and you'll be just a grumpier person if you just find yourself struggling with resonance and not having just put the time in the beginning to become a pro at it. Okay. All right. So now let's talk a little bit about hybridization. I'm going to do this very quickly because I think I'm spending too much time on the small stuff and we have a lot other cooler stuff to get to. Okay, so assigning hybridization. The general rule of thumb is if we were to look at this carbon, here's the way I like to do it. Carbon has a 2s and 2p. This is what carbon's valence looks like. 4 valence electrons, we know that. That's a carbon makes 4 bonds. So when carbon goes to bond with other stuff, right, what essentially in a nutshell carbon will do, or in the hybridization bonding theory, is that, in a bond, carbon's going to meet another atom halfway and say, let's each put 1 electron into this bond, we'll share it, life will be great. That's a little hard to do that right now because this orbital is completely empty. This looks good, and this is full. And also, you're going to see that I didn't draw these at the same height because the 2p is a little higher energy orbital than the 2s. So what carbon does is when it finds someone it's going to heat like carbon will bond with, it takes all of these valence shells and it makes them basically throws them in a molecular blender, spins it up, and depending on how many bonds it's going to make with carbon, it will produce, let's say in this situation, right, we're going to make 4. 1, 2, 3, 4. Carbon's like, I'm going to take my 2s, my 3 2p's, and I'm going to make 4 sp3 orbitals which makes sense because they're all equal energy, because they're a mixture, they're all the same, and it's 1 part S, 3 part P. That's why we get sp3, which, if you're even thinking ahead, has 25% P character, 75%, or sorry, 25% S character, 75% P. That's hybridization. So if someone ever asks you, what's this carbon's hybridization, which sometimes you'll just need to be able to look at something and just know, is I like to look at the number of bonding areas and then just basically go, all right, 4, I need an S, a P, a P, a P, sp3. So for example, if we looked at something like this carbon right here has 1, 2, 3 bonding areas. So I need an S, a P, and a P. This carbon's hybridization is sp2. Now, to go a little bit further, I'm talking about this is the hybridization of the sigma bonds. A sigma bond, right? If I look at this carbon, I look at this oxygen, carbon's basically saying, all right, oxygen, I want to have a head-to-head bond with you. That's a sigma bond, a head-to-head orbital overlap. And the orbital that I'm bringing in that has 1 electron is an sp2 orbital, okay? Oxygen does not have to come in with the same thing. It can come in with something different. However, if we look at oxygen and we look at its hybridization, and lone pairs count as a bonding area as well, this oxygen has 1, 2, 3 bonding areas, so that means this oxygen is also sp2 hybridized. So oxygen's coming in here with 1 electron for the sigma bond, and that is an sp2 orbital as well. Okay, so I wonder, you guys might be curious, you might be thinking, where's the extra P, Joe? Because if we have an sp2, that's 1s, that's 2 p's, well what about this 1 less lonely P orbital? Well, this is a double bond, right? A double bond consists of a sigma bond as well as a pi bond, right? So we've drawn the sigma bond, let's draw the pi bond. So as opposed to having these like head-to-head orbital overlaps for sigma bonds, pi bonds are these, people like to call them like cotton candy, loopy, orbital, like dumbbell type things. It's a p orbital. Pi bond is 2 p orbitals that are parallel to each other. Literally, they have to be like this, parallel, 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 not this. This is a no-go, this is a send. So just like the sigma bond, they're each gonna have 1 electron there, and there's no head-to-head overlap. They're just gonna have this parallel interaction right here. So obviously sigma bonds are stronger, they're harder to break because you physically have an orbital overlap. Pi bonds easier to break because they're not head-to-head overlap. Okay, so this, what we just drew here, is called a molecular orbital diagram. I've definitely seen this on first exams that you have to draw these. So what we can even do, we'll draw one more. We'll actually go through, like, we'll just say, like, all right, we're going to draw a molecular orbital diagram. And then we can keep on chugging and chugging. All right, so if I just wrote that, I'm going to erase it. Okay, so let's just say someone gave us this structure right here. And let's say they wanted us to draw the molecular orbital diagram for this carbon, and this hydrogen, this network of 3 atoms. So let's do it. So if we look, one of the first things we need to decide is, what's the hybridization of the atoms we're dealing with? Here and here, we have 1 and 2 bonding areas, right? So if we're looking at our orbitals that we have eligible for us to make hybrid orbitals, this carbon only needs 2 of them. This carbon is sp hybridized. This carbon also sp hybridized. And it's so funny and silly to think, but that hydrogen only has 1 bonding area, and it only has an S, the 1s, but it is S hybridized. Not really hybrid, but that's what its configuration is. Okay, so I'm going to go ahead and draw a carbon, hydrogen. So in this triple bond, right, we're just going to ignore this half over here. In this triple bond right here, right, we have 3 bonds. You always have a sigma. If things are connected, there's obviously a head-to-head overlap, right? Sigma, which means that's 1. And that means in this, since it's a triple bond, right, not only do we just have the 1 pi, but we have a second pi. 2 and 3. Yay. Cool. All right, so let's draw everyone's sigma first, and then we'll get the extra bonds thrown in there as well. So right here, I know this carbon and this carbon, this is sp, this is sp, 1 electron in each. There's a sigma there. So this carbon right here, obviously he's coming in with an sp orbital, but we know, and I'm going to draw this a little closer to make it realistic, but hydrogen is just coming in with that s orbital, right? So now we have everyone actually physically connected, which is good. The only other thing we have to do actually is draw the 2 pi bonds that exist in the triple bond. Okay, so this is key. Pi bonds have to not only just be parallel, a p orbital has to be parallel with its partner in the pi bond, but if there are more than 1 pi bond, sets of pi bonds have to be perpendicular. So it's weird to think, but just bear with me. Right here, we have this p orbital and this p orbital. They're a pair. That's 1 pi bond. And if you think about it, like, this is actually in the plane of my board, right? So like these guys would be literally like this. And just like in a graph, like we throw it back to math class, right? This is a 90-degree angle, right? So is this right here. The pi bond to this sigma right here. 90 degrees, that's great. We need to add another set of p orbitals in there. Well, it's the only other way. So this new pi bond needs to be perpendicular to this p orbital, like these p orbitals as well as these orbitals. The only way for us to do that is if we draw this like coming out of the board. So, because that would be the only other way to make that work, if that makes sense. This is like a very poorly drawn z-axis. So, what I'm gonna do is kind of like loop this thing like out like it's coming at me, and then have this thing very small, kind of like it's going through the board, the back of the board. And then I'll do the exact same over here. Okay. And then of course your molecular orbital diagram gets a little messy when you just try and style it and show who's talking to who. Okay, I hope that makes sense. This is a very common thing I've seen on tests, and it's a shame because it kind of like seems scary at the outset, but it's really simple. You're just assigning hybridizations, then actually physically drawing the sigma bonds, and then adding in the pi bonds if they're there. Okay? All right, that's molecular orbital diagrams. Okay. Let's keep going. Lots to do. Okay, so the next thing we're going to talk about, and I'm going to try and make this efficient, but I think it's time well spent, is we're going to talk about acid-base stuff, because this, just like resonance, never goes away, and I feel like it's unfortunate when I've worked with kids who they know their stuff, but sometimes the new things they're learning are harder because they still have like shaky acid-base basics. Okay, so in acid-base world, in OChem, there are 5 kind of rules, especially when you're considering equilibriums, like if you're looking at an acid-base thing where you have this A plus B goes to C and D, and there's arrows going back and forth, and you have to pick which side is kind of the favorite equilibrium. So the first is electronegativity. So I'm just gonna, the way I like to kind of go through this is just go through the 5 rules, show an example with each one, and then maybe we can do like 1 or 2 examples to kind of like show what you might see on a test. But I've definitely seen sections of tests where it's like, here's like 5 acid-base equilibria, and you need to just, for all 5 of them, circle the side that's favored at equilibrium. So I think it's valuable to go through these rules with examples. So for the first one, electronegativity. So let's just say we had something super simple like just water, and then an NH2 minus, a forward arrow, a backward arrow, and over here OH minus, and NH3. Right, so before I get ahead of myself, right, we know this is an acid-base problem because you can see going from this way to this way, right, we have something that is a source of H+, right? And also to introduce this terminology early, right, a hydrogen is nothing but it's proton and neutron and electron, right? But when a hydrogen loses its 1 electron, right, we just have basically a nucleus with a neutron and a proton. So people very commonly, just refer to this as a proton. That's basically what it is. So you can see from here to here, right, there's just a proton transfer. this water basically just lost H plus to the NH2 minus going this way. And the same is true vice, like, backwards. So we know this is an acid-base problem. We need to decide, we need to use our knowledge of our acid-base rules in OChem land to basically figure out which side is favored at equilibrium. So, knowing you guys have a periodic table, but nitrogen, oxygen, and fluorine round out the one row of the periodic table, and we know there's a periodic trend that the more top right you go on the periodic table, the more electronegative you get, right? And I bet you'd even just know that oxygen is more electronegative than nitrogen. So, knowing that, but the reason that that's important is because on both sides, right, and I'm going to keep saying this over and over again, nature likes stability. Nature wants things to be stable, low energy, because things don't react, then everything's cool and copacetic. So we basically need to figure out who can handle this negative charge better, nitrogen or oxygen. And electronegativity comes into play because the person who's going to handle that negative charge better is the atom that's more electronegative. So I hope at this point you're thinking, obviously, that is the right-hand side because oxygen loves electrons more than nitrogen, so this side is happier, it's more energetically stable, lower energy than this side. So that's how electronegativity works. Okay? So I'm going to go ahead and erase this. We're going to move on to rule 2. So next on the list is size. Okay, so very similar, a small kind of example. I'm going to go with so basically we have H2S and hydroxide on one side, and then on the other side HS minus and H2O. So to give you guys a little bit more, like a little snippet of the periodic table yet again, is that in the same column, oxygen and sulfur, they're in the same family. Okay, so that is important knowledge because going from here to here, we added a new energy level. If you could throw it back to Gen Chem and remember like N like equals 1, N equals 2, that's how many energy levels we have. So there's a whole, sulfur has like 3S, 3P, 3D, blah, blah, blah. It's bigger. Adding an energy level makes the actual sphere that is the sulfur atom bigger than oxygen, right? Like there needs to be more volume in that atom to accommodate all those electrons that could be there. So that's a long way of saying sulfur's bigger than oxygen. So if we're going to look to see who can handle the negative charge better, in this case, sulfur is much bigger than oxygen, which means the negative charge that's on each of these spheres, because electrons, right, they're randomly shooting around the atom, like around the nucleus, there's more room for these electrons to spread out with sulfur. So, because of that, right, because there's so much of the same type of charge that's going to repel each other. However, it can more evenly distribute itself on a sulfur atom than an oxygen atom. So for that reason, sulfur can handle the charge better, which means this side, the acid-base equilibria, is favored. Okay? Cool. So it's important when you look at acid-base equilibria problems, you're going to need to kind of digest what atoms are present and what relationship exists between the atoms that are harboring negative charges and whatnot. Okay, next one is resonance. Our dear old friend is already popping back into our lives. Okay, so this one's extremely obvious to see, like crazy obvious. But so we can do something like this. Side, but whatever. All good. You know what? We'll even. That's ethanol. I'm gonna make this area a little smaller. There we go. Gives me a little bit more room. Cool. Okay, so we have ethoxide, acetic acid, ethanol, acetate. Okay, so what we have going on here, obviously this oxygen would be ripping off this H right here, going this way, which is why this H kind of ends up here, and the oxygen gets a negative charge. So I hope what you're seeing, what's screaming at you, is over. So we need to compare these two, right? Oh wait, whoops, yowza. Ethoxide right here. We need to see who can handle this negative charge better. And I'm now realizing I'm not doing a great job of introducing the terminology, right? But over here, this is our acid. Right here, this is our base, going this way. And right here, this is the conjugate acid, conjugate from the base. And then this is the conjugate base over here. Okay, so we need to look at the two bases. Who handles the negative charge better? And I hope what you're seeing is right here, this negative charge is static. It's on that oxygen. It's not going anywhere. However, in acetic acid, I hope that you're seeing this oxygen right here. Because of the fact that we have this double bond next door, if we swing these electrons down like this, and we kick these bad boys up here, and we remember to draw our double-headed arrow and say, hey, look at us, we're drawing resonance. I made a double bond here, and now a single bond up here with 3 electron pairs, right? This oxygen is not completely stuck with all those electrons, right? Unlike this oxygen, he's down the river without a paddle. He is putting the team on his back, handling those negative charges by himself. However, this situation, the double bond allows this oxygen to share the electrons across the 3 atoms right here. So, long way of saying, this base is more stable, can handle the negative charge better. This side overall is more stable as a result. This is the side of equilibrium that is favored. Okay? So it's resonance. Resonance is a big one. Resonance is like the automatic win. Okay? All right. So, resonance, very obvious. Gonna keep pushing on. Okay. And it's good that we talked about hybridization because that is the next rule, hybridization. Okay. So, so I know this is probably a very bizarre looking acid-base problem to you because because basically if we're going to draw some arrows for fun, what basically happens is the negative charge on this carbon with the triple bond, these electrons literally grab him, lone pair gets dumped here, and that's how the arrows proceed. The sp carbon right here is just ripping that proton off, electrons going there, but carbon can do that, so it's not totally weird. Okay, point being, we need to see if this carbon in the triple bond or this carbon in the single bond handles the negative charge better. Okay, the relationship thing we have going on here, it's very obvious. This is part of a triple bond, this is part of a single bond, so that's the same thing as saying the hybridization is different. This carbon right here is sp, because the lone pair counts as bonding area, right? So 1, 2. This carbon, we don't see these, but he is 1, 2, 3, 4. He is sp3. Okay, so here's the longer explanation that you never have to write on the test because I'll give you the short and sweet way of explaining it. However, this carbon has a hybrid orbital that is housing this lone pair, right? And that hybrid orbital has 50% s character and 50% p character. Same thing is true over here, right? Hybrid orbital is going to house that electron pair, except there is 25% p character, sorry, s character, and 75% p character. So that makes a difference, and here's why. The s orbitals are, anytime you add an energy level, they are filled first, right? There's the 1s, there's no 1p, then there's the 2s, then the 2p. The s orbitals are always closer to the nucleus. So, closer to the nucleus means closer to the protons. So because of the fact that the orbital that houses this electron pair has more p character, these electrons are closer to the nucleus where the protons live, and because opposites attract, that electrostatically stabilizes the fact that this thing has a charge, right? Because if it has a charge, it's reactive. These electrons are happier being closer to the nucleus than these electrons are over here because the p orbital is farther away. So since there's more p character here, these are farther away. Long way of saying, and here's what you can say on test. You could say like electrons in orbital with more s character, more stable. Some teachers might want the full thing, but like unless they specifically ask you why, you can just say more s character, and then it's good to go. All right, so hybridization is definitely a thing. So obviously these electrons would be happiest in an sp situation, but even if this was a double bond like this, right? This would be sp2, still more s character than over here, right? This would be a 33% s character. Okay, awesome. All right, one more, and then we are done with acid-base land. We can do alkane-related things, like naming. So hold your excitement, it's coming. The high octane stuff. See what I did there? High octane. It's weird when you make a joke in a room all by yourself and nobody laughs. Okay, so inductive effect is the last one. This is the most obvious, so you'll know this right off the bat. And I'm not even going to do an equilibrium for this one. I'm going to kind of do something like this. Okay, so we've basically the same identical structures here from a carbon perspective. However, there's something glaringly different, right? There's 3 fluorines here. The question that if you are posed with this would be kind of phrased like this. Would be between the starred the starred hydrogens for both structures, which structure has the more acidic proton? So think about this. More acidic, the most acidic, is pretty much it. So these are both acids, right? They can both donate H+. To be a really, 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 really good acid, that means you really want to donate H+. So we can say this a little bit differently, is if you're a really good acid and you want to just give your proton to anybody, that means you are going to be, that means the corresponding conjugate base, and I'll draw the conjugate bases here, are very stable because nature likes stability. Nature doesn't do things that doesn't make sense for it. So if an acid really wants to donate H+, that means that the corresponding conjugate base it becomes is very stable, and that's good. Stable, weak, yep, all good to go. So between these two, right, the answer is that this structure is better, and here's why. We end up with a negatively charged oxygen in both situations, right? We know fluorine, super electronegative, right? So much so that not only does this carbon right here have a really, really big partial positive, that's the little lowercase delta, these suckers are so strong, they're gonna steal electron density from him, also from this carbon, which is good because the fact that he'll be more positive than usual means he's sitting next door to this guy that just became negative. That is gonna be electrostatically favorable. Okay, hope that makes sense. So it's because this situation has these fluorines and this does not, which makes this acid more likely to donate H+, which means it's a stronger acid, right, than this, which means that the conjugate base is weaker, which is which is the same thing as saying this is more stable than this, right? So remember that these two are the same. They mean weaker and stable, same thing, okay? All right, if you can internalize those rules, then you're going to be looking real good in terms of acid-base, and I really encourage you to get very comfortable with them because acid-base stuff, when we get farther down the line, when you're doing mechanisms in OChem, acid-base stuff, it's so prevalent and it happens so often in a mechanism. Sometimes you have to drop H+, gain H+, and if that part of the mechanism is challenging for you, then the actual new thing you're trying to learn is just going to be so much more difficult. Okay? All right. So we will leave Gen Chem alone for a bit. It will come back at the very end of the review session, but let's take a break and let's get involved with some of the alkane stuff, which is, in my opinion, what is going to be a little bit, it's obviously newer, brand new information if you're taking OChem for the first time. Okay, so flip my hand to the page. Okay, so before we go into that, you're gonna probably at some point on your first exam get a structure, get like a big structure with a lot of functional groups in it. Just memorize your functional groups. It's easy points. Literally, it's like the point basket coming up to you, and you can reach it if you want, but you can only reach it if you memorized your functional groups. Only thing you could possibly get kind of screwed over by is if I just draw something like this. Just make sure that if you look at this, you don't accidentally call it a ketone, right? This is a ketone, this is an ester, so just be careful of that. And then I don't know if just make sure if you see something like this, you know it's a nitrile. Just little stuff, just memorize them. Just find a chart online, or maybe there's one in your book, or your teacher gave you one. Just make sure you know them, okay? All right, functional groups, consider them learned. Okay, so we're gonna get into naming. I wanna do a quick review of common naming and then do a system like an IUPAC systematic naming problem, because your life will be so much easier if you know common names for that. So really quickly, if we look at a 1 carbon thing, if we add on like a halogen like this would be methyl chloride. You'd have to make sure you figure out how many carbons there are, 1 in this case, so we know it's going to be meth, this is methane. You would just chop this off, add the YL, and then the halogen right there, okay? So if we do 2 carbons, so there's only one position, these positions are the same, right? There's only one place to add something, right? So what you could do is you could have this, right? This would be, since we're doing ethane, this would be ethyl chloride. Ethyl chloride. And so then nothing interesting there. We can just, this would be ethyl alcohol, this would be ethyl amine, list goes on and on. However, things get a little bit more interesting when we bump up to propane, when we lengthen our carbon chain from 2 to 3, and I'll show you why. So we have 3 carbons right here. These positions are equivalent, they're the same. So if I attach something here or here, that doesn't matter, it's the same structure. However, this is not, this is different, which is why I'm drawing a box around it. So if I add something like this onto propane, this is propyl chloride, right? Or this would be propanol, or propyl alcohol. However, if I were to do this, we basically need some other way to tell someone, hey, by the way, I'm talking about a 3 carbon chain. However, the thing I'm telling you is attached to it, it's not on the end, it's in the middle actually. So we add this, we use this prefix, this is the iso position. So this would be isopropyl chloride. And then if we also do this, isopropyl alcohol. Okay? So, the iso position. Remember this prefix. However, and then the last thing we'll talk about is 4 carbons. So, when we have 4 carbons like this, these positions are the same, these positions are the same. Okay? So we could have, this is butane, right? So this is butyl chloride, okay? And this would be butyl alcohol, butyl amine, you get it. So we need, just like this iso prefix, we need something to tell someone we're doing chemistry with, oh, by the way, I have 4 carbons all in a straight line, but I also have this thing attached on one of these interior carbons, not one of the terminal carbons. So, and I always forget to kind of explain this before I get into this, and I'm sure you know this already. So we can classify things in OChem. We can talk about carbons based on how many other carbons they're attached to. So this carbon, since it's attached to one other carbon, this is a primary carbon. This one that's attached to 2, this is a secondary carbon. And then you can do tertiary, quaternary, and then if you just had CH4, you could just say this is methyl. So methyl, primary, secondary, tertiary, quaternary, okay? So because these are both attached to 2 carbons, whenever we would have something like this, not that, this is sec-butyl. That's how you say you have this with something attached here. Sec-butyl chloride, okay? So sec-butyl alcohol, sec-butyl amine, all of that, okay? So I will say, because we're almost done with the common naming stuff, but we have a little bit more work to do with butane rather, because we can have 4 carbons in a row. However, what if I draw 4 carbons like this, right? This is a completely valid standalone structure. And it's kind of cool, because, not cool, I think it's cool. It plays in with exactly how we would use this. So when we have 3 carbon chains like this, right? And with something attached to the middle, this is the iso position. So we wouldn't say isopropyl methane or something like that, because we have 4 carbons. This is still a part of the butane family. This is regular butane, or you might hear people call it N-butane. This is isobutane, okay? So just make sure you know isobutane. And on isobutane, I hope you can see these 3 positions are the same. This one in the middle is different from the other 3. So when we have isobutane and we attach something on the end like this, 1, 2, 3, 4, and then something like that, this is isobutyl chloride, okay? However, if we were to move this chlorine to the middle instead, like this, we need some other prefix to kind of describe what that middle carbon is like, and I hope you can realize it is attached to 3 carbons, so people will call this tert butyl, and then whatever's attached, tert butyl chloride, or if you want to be super cool, be edgy, T-butyl, or you're just lazy and don't want to write extra letters, T-butyl, and then what's attached to T-butyl chloride, okay? So, very quickly, if I drew this, I hope you're sitting at your computer saying isopropyl bromide. If I drew this, I hope you're saying 1, 2, 3, 4, isobutyl amine. If I drew this, I hope you're saying sec-butyl fluoride. And if I drew this, I hope you're saying T-butyl alcohol. Okay? Okay, common name. Very important. Don't underestimate it, because people like to use common names in OChem because they like to flash the cool lingo, and you never want to be the person who, whether you're reading a problem and they give you the common name and then you don't even know what structure to work with, that always sucks. But also you want to be cool. You want to know the lingo. So let's look at this problem. Now we're going to do a systematic naming problem. Okay. I'm going to go through the whole process of numbering, finding the longest chain, naming substituents, alphabetizing, which always seems to be the hardest part. Okay, so, looks big and scary, or if you don't think it's big and scary, that's even great, but this is not a bad problem. Okay, so when we have a big structure like this and someone is saying, come up with the full systematic IUPAC name, the first thing we need to do is find the longest chain. The longest chain is what you're working with. So, biggest pit trap I would ever fall into is just because we read left to right. I start only here and go this way, and I sometimes forget to try different routes. So make sure you find the longest chain. You count every possible route. So let's look at this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 11's this way so far. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. 11 seems to be the longest, and this is not 1, 2, 3, 4, 5, 6, 7, 8. So 11 seems to be the longest. However, we have a tie, right? The way you break a tie is you would count both chains for both ways, and you want to see where the most amount of branching happens at the smallest number. So 1, 2, 3. So it starts on 3, and then if we even go this way, 1, 2, 3, 4. So they both come this way. So we're definitely at least going to consider this route. So this way 11 starts at 3. 1, 2. Okay, so this chain is going to win because our branching happens at 2 as opposed to 3, which is why we win going this way. So I'm going to finish numbering 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, cool. So what I like to do is once we found the longest chain, I just like to go and just at every place where we have branching, just name that individually, write them all down, then we can alphabetize them, then stick the name together, okay? So at 2, right, we have these methyl branches right here, right? We have 2 of them. So we have 2 here, we have a methyl branch here, methyl branch at there as well. So we're gonna get 2, 2, 5, 7, we use a prefix to describe how many methyls we have. There's 4 of them. So that's tetramethyl. So that literally tells whoever, once we've produced this name, if I were to have someone else read it, they would know, okay, here are where the 4 methyl groups are, okay? So at 3, we have an ethyl. At 7, we have a bromine, but we would you do that as bromo, just like you do chloro or fluoro. And then at 8, this is where our hard work pays off in common naming land. I hope you're looking at this and saying, okay, I see 1, 2, 3, and this little 3 chain, 3 like carbon piece is attached to the middle. That is an isopropyl group. Okay, cool. So we've labeled all of our stuff, and what you need to remember is that the di, tri, tetra, these prefixes do not count for alphabetizing. It's things like and neither do sec and tert. These do not count towards alphabetizing. It's things like iso, cyclo, and I don't know if you guys have ever run into this, or neo, but these actually matter. So looking at this, our first thing we're going to put in the name is definitely bromine, right? Because we know the alphabet because we're smart. Bromo, then we're going to go with ethyl, then isopropyl because of the I, and the M for methyl will go last. Okay? So we have the order that these need to be in. Our parent chain is 11, so that is undecane. Make sure you know those. Up to 20. Anyone that goes above 20 is kind of mean. So let's write the name. So we start with 7 bromo, and then a dash. You always separate numbers and letters by dashes, and then additional numbers by commas. So 7 bromo, dash, 3 ethyl, dash, 8 isopropyl, and then we got a dash, and then we got the 2, comma 5, comma 7, dash, tetramethyl. And then words, you just stick them all together. So literally run the tetramethyl straight into undecane. Okay, there you go. That's your name. The only other way this can get harder, the only way, is if you have to name something in parentheses. I'm not gonna do a problem. I can't remember if I have a video on naming in parentheses on Jochem, but, and I can make one. But that's the only other way this gets difficult. Other than that, it's just finding the longest chain, making sure if there's a tie, break the tie by branching. Then you want to, label your substituents, alphabetize them, put the name together, bam, done. Okay. So, I'm gonna erase this. Okay. That is it for naming. All right, so the next thing we're gonna do, so kind of where I wanna go with the rest of this review session is a Newman projection problem, a cyclohexane problem. Actually, you know what, we're a little short on time. Probably just gonna, Newman projections aren't terrible. Just gonna do a cyclohexane problem and then get into the free radical chain reaction stuff, okay? So, in the lovely world that we live in, well, I'm sure you've talked about the fact that, so we have a couple, you've seen cyclical structures in OChem. Cyclo Butane, Cyclo Pentane, Cyclohexane. This right here, so there's one thing that can make a structure's internal energy high is when bonds aren't given the correct and freedom and flexibility and angles to correctly exist. This, in this case, when that's in a cyclical situation, this is called ring strain. So cyclobutane is a very high energy structure because it has a lot of ring strain because these carbons are sp3. They want a oh my god, I cannot remember the geometry. They want to look like this. Tetrahedral, sorry. Oof, it has been a Sunday. They want to be tetrahedral. They want to have 195 degree bond angles. When you have a square, we're smart people, this is 90 degrees. The fact that these bonds can't get to 109.5 degrees makes this structure unstable, high energy, because there's strain there. It wants to be, the structure wants to be a little wider. It almost wants to look like this. If it gets to 109.5. Cyclopentane's a little bit better, right? Because we obviously have an extra atom in the ring, gets a little wider. I forget what the angles are here, but there's a little ring strain. So if we look at ring strain, this is the most, and this is the least. Cyclohexane has no ring strain because it has 109.5 degree bond angles. That's why we see so many hexagons in nature, because this is it. This is it, ladies and gentlemen. Okay, so that's why there's a whole chapter devoted to cyclohexane in a book, like in your textbook. So what we're going to look at is you'll get problems where people will put substituents on cyclohexane rings, and you will need to draw. I know you guys are probably familiar with chairs, but there's a way. So like cyclohexane doesn't exist like this flat on paper in nature. And I don't have a model kit, but it likes to exist in a chair conformation. And people call them chairs because you can draw a funny stick figure guy, like he's at the beach, hanging out like that. So, 1, 2, 3, 4, 5, and 6. I was awful at drawing chairs when I first took OChem. I had a teacher, Erica Houston, who came up with a really awesome way that I think is completely foolproof to draw a good chair. Draw an upside down propane, come down from the middle, this right here, draw a regular propane, connect the dots. Wonders. It's not the best, but it looks legit. Okay, so example problems you would see on a test is if, actually what we'll do is I'll just go ahead and put one substituent on this cyclohexane ring, this methyl CH3. So what we need to realize is on rings, at every position you can have a wedge or a dash. A wedge is actually this coming out of the plane of the page, board, whatever you're working on, coming at you, and a dash is something going straight through the board. We're talking like 3D in space. So if I were to draw the chair, like the chair conformation for this right here, this methyl cyclohexane, I'm just going to go ahead and draw the methane here, right? Because it just doesn't matter which position I put it on. So on chairs, this is a peak, this is a valley. You know what a peak and a valley is, because peaks here, like you go from a peak, you're up, then you go down to a valley, then you go up to a peak, you go down to a valley, up to a peak, down to a valley, back up to a peak. At peaks, you have what is called up axial and down equatorial. At valleys, you have down axial and it's slightly up equatorial. So like it's better, I'm going to display it down here. Down axial, slightly up equatorial, slightly up, okay? So at this position right here, we have an up CH3, an up methyl, and then a down hydrogen. So the up, and this is axial, and this H is equatorial, okay? So chairs can exist in two conformations. You can have a chair flip is what it's called. So, I don't know, you can draw an arrow like this if you want to. I'm actually going to draw like this. I'm going to draw it down. So, you still do your upside down propane. However, instead of drawing this like this, draw it the other way. Go left, can make your chair like this. It's important to know that the numbering stays the same. So this is 1, this is 2, this is 3, 4, 5, and 6. So basically every peak becomes a valley and every valley becomes a peak. So if this is up stays up and down stays down, but what changes it is axial and equatorial. So this now, position 1 is a valley, so up is equatorial, down is axial. We have a down axial H and an up equatorial CH3. Okay? So that's how this works. So what is important to know, because someone's going to ask you is, they'll probably ask you to draw chair conformations of cyclohexane, and then they're going to ask you which one's more stable, which one is energetically favored, like in this chair flipping equilibrium, because it goes back and forth, back and forth, back and forth. So if I draw an energy diagram, and I was really bad at kind of interpreting these sometimes, but literally this is increasing energy, and said a different way, increasing energy means more reactive, less stable. So this would have been great to talk about Newman projections, but you guys are smart, and I bet you guys handle Newman projections well. When things are axial, you have more of these interactions like this, where these electrons here are repelling the electrons here. There's more like steric torsional strain. So when things are axial, you get more instability in your chair. When you're equatorial, these types of things don't happen. They actually are, like it's, here I can draw this really quickly. This CH3 and this H are eclipsed right here. There's strain right here. But down here, they would be like this. They would be staggered. So that's why equatorial, from an energy perspective, equatorial is always better than axial. So whenever you do cyclohexane stability problems, and we'll see this even more with multiple substituents on your chair, you want to put anything big, substantial group-wise, if it's highly branched especially, equatorial instead of axial in your chair. So I think it's easy to see that we're going to have something here and something here. And it's, if I call this A and I call this B, A is, I'm not saying this is like a large thing, but I'm saying A is higher energy than B because of the axial methyl group, and then it's lower energy B because that methyl group is equatorial. Okay? So let's quickly do something like this. We'll do an example where we have more than one substituent on your cyclohexane ring, and we will draw both chairs, evaluate who's stable, and then we'll move on to the last part of the review session. Okay, cool. So if we look at this, I'm going to draw a T-butyl group, and then over here I'm going to draw an ethane. Okay? So my first chair. So I'm just going to call this 1, 2, 3, 4, 5, and 6. What's important to note is that we have a 1-3 relationship between our T-butyl group and our ethyl group. So right here, I'm going to put T-butyl here. There's going to be 1, 2, and then 3. So I hope you can see that our T-butyl group is up, and up at this peak is axial. And at position 3, we're also at a peak, which means down is equatorial. So up looks like this, down looks like that, just slightly down like that. It's kind of weird to draw. Okay, so let's chair flip. I'm gonna draw my propane the other way. So remember, these are the same. So this T-butyl group is now at a valley. Up is still up, down is still down, but what is axial is now equatorial. And same thing at 3. Our ethyl group is still down, but down here, this is valley, peak, valley. Down is axial now. So I hope you're looking at these two chairs and you're thinking to yourself, easy money. It's very obvious. The T-butyl group is highly branched. It causes a lot of steric strain, torsional strain. We want to put that sucker equatorial. You would say this is the less stable, or sorry, this is the most stable, most energetically favorable chair conformation. Or if someone asks you what's the least stable, higher energy conformation, you pick that. Okay. we're now to pros with cyclohexane chair conformations. Okay, so I want to spend a little bit more time on this. I'm going to try and efficiently explain everything. We're going to go over the mechanism for the free radical chain reaction. This is the only mechanism you need to know. This is your very first reaction, so I hope it has a special place in your heart. But know it like the back of your hand because you're going to need to very reliably show someone that you're a pro at it. Okay? So let's very quickly, if we did the reaction of ethane, and then we do Cl2 and then light H nu, we're going to go from ethane to ethyl chloride. Okay, so I'm going to efficiently go through this mechanism, but make sure you guys can sit down and just produce this thing from scratch like it's the back of your hand. So remember, we're going to have initiation, and then 2 steps of propagation, and then termination. So initiation is when the light actually shines on the chlorine that you have, or bromine, and since this bond is super weak, the light puts in enough energy to actually split that bond, to cleave that bond, and the way it breaks is that each chlorine gets 1 electron, so I'm going to draw 1 arrow going to chlorine with a single head, right, because we're only showing 1 electron moving, and I'm going to do the same thing over here. So remember, this is homolytic cleavage. Cleavage because the bond is breaking. Homolytic because it's splitting in the same fashion. One electron to both parties. Does that make sense? Okay. So I'm going to draw this up here a little bit and box this. Okay. So this produces 2 chlorines, but not even just 2 chlorines. They're radicals. A radical is something with an unpaired electron. Very reactive, right? So that's why this is going to initiate our reaction. So I'm going to go propagation 1, P1. What happens here is we're going to get our alkyl piece, the alkane piece, is going to bump into a chlorine. And what chlorine is going to do is it's going to find a hydrogen that it wants to interact with, and it's going to say, okay, hydrogen, I want you to leave this carbon, so bring 1 of your electrons, come over with me, and let's make a bond. That's very key, and that was something that really confused me for a bit. It's not like chlorine's just going to grab the hydrogen. The hydrogen has to leave with 1 electron, which is why you see him leaving with 1 and me linking up with chlorine. So we showed 1 electron leaving this bond. We actually have to physically show the other one going and landing on that carbon. So we do make some HCl. We don't really care about that. What we care about is the fact that we made a carbon radical, which is good. And we do have 2 other hydrogens here. They're there, just drawing them for clarity. So in P2, because I bet you're wondering, we need to actually make this alkyl chloride. We have our carbon radical, and this was another mistake I used to make a lot. It's not going to bump into this second chlorine radical over here. It's going to bump into another Cl2, and just like in the above step, the carbon is going to link up with one of the chlorines, and then the other chlorine gets 1 electron. And this is so key that you show it this step and not have this link up with one of these. The point being is that this reaction is a chain reaction, because by the nature of doing initiation P1 and P2, we actually produce this. And that's what the whole, we can start the reaction the moment initiation happens, and then it keeps going because it produces the very thing that gets the party started in the first place. So it's a self-sustaining reaction. Once it starts, it's a steam train going straight ahead, okay? So that is how it goes down. Oh, so that's P2. Someone may ask you to provide a termination step. Termination step is just when 2 radicals hit each other, which if you get enough termination, which eventually happens, right, your reaction stops because you have no more radical to get the thing going. Termination step, there's so many of them. This is a termination step. The really classic one to draw is a chlorine radical hitting another chlorine radical. There's no wrong termination step unless you draw it incorrectly, but know this reaction like the back of your hand. You're gonna be asked to do the mechanism. That's just a fact. Okay? So what I want to do is erase this. I'm not going to do I'm not going to draw the full bromination mechanism because it's exactly the same. But what I want to talk about before we call it quits for today, for this live review, is the differences between chlorine and bromination. Chlorination, bromination, because chlorine's a bit pickier than chlorine. To understand that, we need to understand hyperconjugation. And then I want to wrap things up with Hammond's postulate. Okay, so if we looked at this reaction, people usually write this like this. So bromine and chlorine. Bromination requires a little heat to get things going. Chlorination does not. What's important to know, and you could look at bond dissociation energies, you could look at the actual more detailed thermodynamics of this reaction. What's important to know is that this is more exothermic because some of the bonds in here are easier to break. That costs less energy to break than the bonds in here. This is like that, less exothermic. There's even one step in here that is actually endothermic, which means like you have to put energy in. It's not like, it doesn't like give off heat. So what is important, and what I guess to lead into this conversation I want to start, is if we had this reaction, I don't know the exact numbers, but you get like almost a 50-50, around like a 50-ish, 50 split of this. If you did it with bromine, you literally get like essentially 99.999%, a lot of just the iso product. So it's this that I want to talk about, this phenomenon, okay? Phenomenon, okay? So before we go there, I need to explain what hyperconjugation is. Okay, so in the reaction, I think let's look at this step. Let's just assume let's look at this reaction, this step in chlorination. Yeah, we'll just look at chlorination. So there's a step in each of these mechanisms where to produce both of these products right here, we would need to produce a radical at this position and at this position. And this is this step. It's where chlorine would come in, he abstracts the hydrogen, and we produce the radical right there. So what I want to talk about is, so since we are forming the bond here, but we have to put energy in to break the bond here. And the radical here and the radical here differ in that this is on a primary carbon and this is on a secondary carbon, okay? So if we look at the hybridization of both of these carbons, single electrons count as, they don't count as a bonding area. So at this point, this carbon right here, 1, 2, 3, radicals are sp2 hybridized. So if we wanted to draw like what this would look like on a molecular orbital diagram level, I'm gonna use this one for example. I'm gonna kind of draw it as if I'm looking at it like this, sideways. Since it's sp2, we have a leftover p orbital in both situations, and that is where the radical electron lives, okay? So radicals make molecules reactive, not stable. There is this stabilizing effect when you have a radical called hyperconjugation, which is a super big word that definitely makes you feel smart. So definitely feel free to whip that out right after we talk about it, because you'll know all about it. So hyperconjugation is sort of pi bond. We have a set of p orbitals that are parallel to each other, right? And that is the stabilizing force. That's their connection. So with hyperconjugation, right, the idea is we only have a single p orbital here, right? There's no matching buddy p orbital. However, next door to this carbon is the CH3. And this carbon has like a sigma overlap between its hybrid orbitals and the corresponding H that's there, right? Because it's a CH3, so 3 hydrogens. There's free rotation on single bonds. They're just spinning all the time. In a blink of an eye, at an instant in time, this p orbital will be parallel with this set of orbitals that are in the sigma bond, and they mimic a pi bond. So for an instant, there's this stabilizing effect, right? It's only for an instant, but it's there. So the more, and you can see that we have the exact situation going on here and here. So there's like 1, 2, 3, and then another 1, 2, 3. There's 6 opportunities for hyperconjugation to occur at any given moment for this radical electron sitting in that p orbital, right? So the more carbons that are attached to a radical, the more stable that radical is. Because if you look up here, this radical only has one neighbor, and there's only 2 hydrogens there. So the opportunity for this to have to benefit from hyperconjugation is, since there's 6 here and 2 here, 3 times more likely here. So secondary radicals, so radical stability goes like this. Tertiary is greater than secondary, greater than primary, which is much, much, much greater than methyl. The takeaway is the more neighbors you have, the more stable you are when you are a radical. That's hyperconjugation, okay? Had to explain that to come back to this to say, remember, nature doesn't do things it doesn't like. But you can make nature do stuff like that, but you have to supply the energy for it to happen. So because this radical is more stable, this one, than this one, to break this bond, it costs less energy here, more energy here, to produce a primary radical than a secondary radical. So I hope that was the take-home point. So tertiary, secondary, primary, methyl, this is how radical, this is stability. So to produce, it's much easier to produce a tertiary radical than a methyl, because since these are more stable, you need to supply less energy to nature to make it happen. I hope that makes sense. Okay, long way of saying, because the chlorination reaction is much more exothermic, and the bromination reaction is less exothermic. There's like more of an abundance of energy to play with as far as the bonds you need to break in the chlorination reaction than in bromination. So the rule of thumb is, when you do chlorination, you will put a carbon, you will put a chlorine on the position with the most amount of hydrogens. Chlorine's less picky. It doesn't care about what radical it has to make, because there's tons of energy in the energy bank to do it. Bromination is much more stingy. Bromination is going to go to what's called the most highly substituted carbon, which is just a fancy way of saying, oh, I have my choice of primary or secondary. Secondary is more substituted. Substituted means attached to other carbons. So I'm going to go to the secondary position. So to actually put that into action, and then after I do this, we'll tie this even into Hammonds Postulate, and then we'll call it a Sunday. So for example, oh man. If we did Br2, heat and light, on this isobutane, bromine wants the most substituted position, which is clearly, right, because our choices are primary, 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 or tertiary. Bromine, you best believe, is going to be the diva that is going to say, I want the tertiary position. On the other hand, right, if we do the same exact reaction with chlorination, because chlorine's less picky, chlorine doesn't care, chlorine's just there for a good time, he just goes where there's the most hydrogens to pluck one off to make a radical. I hope that made sense. Oh, okay, last thing we need to do. And how am I doing on time? All right, do this real quick. Just a few minutes extra, guys, if you want to hang around. Okay. So, Hammonds Postulate. Hammonds Postulate is the idea that when you have a reaction, let's say like you have A plus B goes to C. If this is fast, or if this is like, if this is fast and very exothermic, or just you know that it's very exothermic and a very quick reaction, Hammond's postulate states, if we draw an energy diagram, that A plus B and C, if we were to draw our energy diagram, right, because we're starting at higher energy, going to less, like lower energy, and the distance here is our delta H, our enthalpy. If this is really, really wicked fast, the transition state, and I'll just say, just label like what we have in the transition state will just be AB. Or, yeah, AB, whatever AB might be. That was too many B's. AB in a very fast exothermic reaction looks more like A plus B than C, because since it's happening super, 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 super fast, we look more like the reactants because there hasn't been enough time for the transition state to really get closer to what C is. On the other hand, let's say we have D plus E goes to F. If this is slow and like not nearly as exothermic, so we have an energy diagram. So we have here to here, E plus F. So this would look like the transition state's earlier. If this is slow and nearly exothermic, then DE, whatever intermediate we have at our transition state, it's going to look more like F. So this would look like this. So it's like slow, 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 slow. There it is. And I'm not the best artist in the world, but that is Hammond's postulate in a nutshell. So if things are super duper duper fast, and like you know that about the reaction, and someone asks you, okay, given that, knowing that about the reaction, what does the transition state look more like, reactants or products? Since it's fast, not enough time has really gone by to let the transition state look more like product. It looks like reactant, and the opposite is true. If it's slower, less exothermic, the transition state will have more time to get closer to what the product looks like, and that's why you and that's how you illustrate that on the energy diagram. Okay, so what I want to do is, I remember seeing an exam question one time that I really liked. It was, I thought, a very good question because it wrapped Hammond's postulate into the whole chlorine-bromine ish. So, really quickly, what I'm going to do is I'm going to blow through this. I'm going to really just draw this just to get it done. But we have initiation, we have, bromine's picky, right? So bromine's going to go for the most substituted carbon's hydrogen. Going to produce this radical. Or you know what? I'm actually going to swap this out with, yeah, because this was what the problem was. Sorry. Switch into chlorine. Sorry. And actually we'll go here. Oh man, what are you doing, Joe? Chlorine. Yeah, chlorine. Okay, here. Oh boy, I'm a mess. H here, got H. Okay, and then I'm just gonna not draw stuff in this time. Okay, plus. So, what I liked about this problem was that they said like draw like the energy diagram and indicate if there's a late or early transition state. And then but it made sure to indicate that it wanted you to do it for this step, the bond breaking step, not this step where there's a giant energetic payoff. So even though we know this is an exothermic reaction that gives off a lot of energy that is fast, what I liked about this problem was instead of saying, because it's multiple steps, it just asks you to do it for this step, which in itself costs energy, is bond breaking, so it requires, and it's not as rapid. This is where all the rapid energy payoff comes. So this step, so even though we would assume for chlorination, it's gonna be an early transition state. What I liked was that this was a late transition state because of the fact that you have to break bonds. So on the energy diagram, all you need to do is just, draw your reactants, your product, and say that is a late transition state, and that you look more like product. Okay, well, gang, thank you for rocking with me. I still have no idea how many people are on this, but this video I will put on JoChem. I will make sure to add a little section for live reviews. And like I said, I hope this was helpful. If you just even tuned in, I don't know, just because you know me or you heard about it from a friend, so if you're not taking OChem, please send anyone that you do know taking OChem towards JoChem. I really want to help people, and I'm going to be spending a lot of time on this project this year. I've been a little bit sluggish the last few years, but I've really been getting a kick in the pants recently, so I'm real fired up, and you're going to do a lot of cool stuff for the project this year. More live reviews to come. Again, follow me on Instagram at JoChem_IO if you like for more information about what I'll be doing, content and tech-wise with the site. If you like funny memes, gonna be some dank memes, and just some of my hot takes about like what I think about OChem and like how it's taught, or like what I think people do that could be better, as like how they try to study for it, or even just like how I feel like OChem has changed the way I think about things. And subscribe to me on YouTube. I need to get those subscribers numbers up so I can actually do YouTube live events. And that's all on my About page on JoChem. Seriously, thank you so much for joining, because I would love to teach OChem for a job, but this is kind of my little outlet for how I get to do it. But like I said, there will be a second live review sometime late October. Like I said, please send me questions for the next one. Let me know when tests are, so I know when to, so I don't just pick a random day and then the review's after your test, and then you're like, well, damn, I would have really liked this before the exam. Yeah, thanks for joining, guys. Have a great Sunday.